There are many scenarios in the real world that are defined by multiple criteria. Let's say you have a job and for the first 40 hours you get paid $15 an hour, but for every hour over that you get time and a half. That is two different functions that define your earnings that you can make. Or if you have ever looked at the tax statement and the guidelines for, depending on what income you have, how much taxes you have to pay. The federal income tax is an example of a piecewise defined function. A piecewise defined function is a function that has different rules for different pieces of its domain. So it is a function that is comprised of different functions all on one graph. Here's an example. F of x is equal to x plus 2 is less than or equal to negative 1, but is equal to x squared minus 1 for x greater than negative 1. Recall our definition of a function. It said for every input there can be only one output. I have a lot of students that, let's say I wanted to find f of 5, for instance. I don't plug 5 into both of those rules because that would give me two output values, which contradicts the definition of a function. And furthermore, 5 only satisfies one piece of that domain. 5 is either less than or equal to negative 1, or 5 is greater than negative 1. Because 5 is greater than negative 1, we're going to use that rule that corresponds to those particular values in the domain. F of 5, therefore, would be just 5 squared minus 1, which is 25 minus 1, or 24. Now if I wanted to find f of negative 1, negative 1 only satisfies one part of that. It is either less than or equal to negative 1 or greater than negative 1. Well, negative 1 is less than or equal to itself. Therefore, f of negative 1 is found by evaluating the first function to get negative 1 plus 2, or 1. So let's go into this a bit to see how you would actually graph these particular types of functions. The way I like to do this is by making two tables, or however many pieces you have in your piecewise defined function. If you have three functions there, make three tables, so one for each part. My first part is y equals x plus 2. So I'm going to have a table for x, and then y equals x plus 2. Then I'm going to have a table for x, but y equals x squared minus 1. Now the thing about this is I can't just go and randomly choose values for x for these two functions. I have to use the restriction that I'm given. The first rule only applies for values of x which are less than or equal to negative 1. So the only values of x that I can choose here is that they have to be less than or equal to negative 1. And for my second piece, these values of x have to be strictly greater than negative 1. So in the first rule, I'm going to choose negative 1. Then anything less than that, so negative 2, negative 3, negative 4. And it might be helpful to draw a number line or look at a graph and figure out, what numbers are less than negative 1. Those would be to the left of negative 1. And then I'm going to substitute those x values into this function to find out what the corresponding y value is. So negative 1 plus 2 is 1. Negative 2 plus 2 is 0. Negative 3 plus 2 is negative 1. And negative 4 plus 2 is negative 2. For the second piece, x has to be strictly greater than negative 1. Now, the problem with that is that there are infinitely many values greater than negative 1 that are between negative 1 and 0. It's very tempting to just go to 0 there because I'm thinking about values greater than negative 1, so a lot of us just see the next integer, which is 0. But I have to represent all of those numbers that are very, very close, like negative 0.9, negative 0.999999995, right? X could technically take on those values. And so what I do here is I actually put in negative 1 in my table, and I'll show you how we deal with that in just a minute. Then things greater than negative 1, so 0, 1, and 2. Then I have to square it and subtract 1. So negative 1 squared is 1, minus 1 is 0. 0 squared is 0, minus 1 is negative 1. 1 squared minus 1 is 1 minus 1, or 0. 2 squared is 4, minus 1 is 3. So on the endpoints, I have to make a determination. And when I say endpoints, I'm meaning at this value of x where the domain is separated, that is where a different rule takes over. I have to determine will I have an open circle or a closed circle. So an open circle means that that point is not included in the graph. And a closed circle means that that point is included. And so the closed circle will be used when you have a less than or equal to or greater than or equal to. Open circle is when I have a strictly less than or strictly greater than. So now I'm going to plot these. On the first piece, notice that x is permitted to be equal to negative 1. So at this point, negative 1, 1, I'm going to have a closed circle because it is a point on the graph. But for the second piece, where x is strictly greater than negative 1, I'm going to have an open circle because that point is really not on the graph, but everything up close to it is. So you'll see on this graph that I have drawn how I obtain this. Negative 1, 1 is where I have this closed dot. Negative 2, 0. Negative 3, negative 1. And negative 4, negative 2. And then I draw the line, which is really a ray, a half line, connecting those points. And notice that this piece does not extend beyond the negative 1, right? All of that piece is to the left of negative 1. My second piece is negative 1, 0, which I have this open circle. 0, negative 1, 1, 0, and 2, 3. And I should recognize that as a quadratic function. A parabola will be the graph, if you remember those basic graphs that we talked about earlier. And so you're going to have a piece of a parabola and a piece of a line. Now if we think about what's the domain and range, the domain, the left piece goes all the way from negative infinity up to negative 1. It includes negative 1. The second piece starts at negative 1 with an open circle, but then goes all the way to the right. But because negative 1 is included, I don't have to make a separation in my domain. My domain is all real numbers. My range, it starts at negative infinity, right? We're reading from the bottom up. And that first piece stops at 1. But then my second piece has a bottom point of negative 1, but then it goes on up to infinity. So my range is also all real numbers here. Now understand, even though there's an open circle at this 0, the other graph actually included that y value. So right, we're just projecting all of the y values onto this number line to see what y values are used in the graph. And so we don't have to make a separation there because it's actually included in one of those pieces. So let's look at some examples. We want to graph these functions and state their domain and range. We have f of x equals x minus 3 if x is less than or equal to 1, or negative 2 for x is greater than 1. So we're going to make a table for the first piece and a table for the second piece. The first piece, my x values are only less than or equal to 1. My second piece, x has to be greater than 1. So to be less than or equal to 1, I'm going to choose 1, and then things less than that, 0, negative 1, negative 2. And we'll go ahead and do this piece, and then we'll go to the second. So y is x minus 3. So 1 minus 3 is negative 2. 0 minus 3 is negative 3. Negative 1 minus 3 is negative 4. Negative 2 minus 3 is negative 5. The second piece is just y equals negative 2, and that's defined for x greater than 1. But recall I need to put 1 here because I can include 1.00001, so I need to know how the function actually operates at 1. Then anything larger than 1, so 2, 3, 4. But my y value is just simply negative 2. It's constant. There is no variation in that. So my y value is always negative 2 for that piece. Now x less than or equal to 1, back to that first piece, because it's allowed to equal 1, we're going to have a closed circle on our graph at that point. X is greater than 1. We can't be allowed to equal that, so we're going to have an open circle. Now we plot these points. 1, negative 2, 0, negative 3, negative 1, negative 4, negative 2, negative 5. When I connect these points, it does form a ray, again, a half of a line, and I cannot extend my graph beyond the 1. The second piece is 1, negative 2, which happens to coincide with this other point, so that's okay. If we put an open circle on top of a closed circle, it's closed. 2, negative 2, 3, negative 2, 4, negative 2. And so we see that there's a piece of a horizontal line that extends to the right of 1. Our domain in that function is all reals, right? As we go from left to right, the graph continues. Our range is we start from the bottom up, the bottommost point, but where does our graph stop? It stops at this value of negative 2. So our range is from negative infinity to negative 2 with a bracket. Another example is f of x equals negative 1 minus x for x less than 2, and negative 5 plus 2x for x greater than or equal to 2. So again, I make my table. I have y is equal to negative 1 minus x, and that's defined only for values of x which are less than 2. Then we have y is equal to negative 5 plus 2x, and that's defined for x greater than or equal to 2. So in my first piece, again, I have to include 2. Sorry, that was just strictly less than. I have to include 2 even though I'm not permitted to equal 2, right? Because I have 1.9999999, which is less than 2 but not equal to 2. So I'm going to have an open circle here. Then things less than that, so to the left of 2 would be 1, 0, negative 1. And you only need as many points to determine what the shape of the graph will be. If I substitute 2, negative 1 minus 2 will be negative 3. Negative 1 minus 1 is negative 2. Negative 1 minus 0 is negative 1. And negative 1 minus negative 1 is really negative 1 plus 1, or 0. Then for the second piece, I'm defined to be 2 or larger. So we'll have a closed circle at 2, and then things larger than that. So let's say 3, 4, and 5. I do notice both of those pieces are linear, so I'm going to have 2 pieces of lines. When I plug in 2, I would get negative 5 plus 2 times 2, or negative 5 plus 4, which is negative 1. Negative 5 plus 2 times 3 is negative 5 plus 6, or 1. Negative 5 plus 2 times 4 is negative 5 plus 8, or 3. And negative 5 plus 2 times 5 is negative 5 plus 10, or 5. Graphing, I'll graph the first piece. We have 2, negative 3 with an open circle. 1, negative 2, 0, negative 1, negative 1, 0. And so that piece cannot extend beyond the 2. Then I have 2, negative 1 with a closed circle. 3, 1, 4, 3, and 5, 5. And so whenever I graph that, I'll have that ray that's continuing there. Well, the domain is everything less than 2 and everything greater than or equal to 2, so that's all real numbers. We can also see that from the graph. The range, it doesn't even start until this negative 3, but it doesn't technically start there. That's open there. And then that leftmost ray continues up indefinitely. The second ray starts at negative 1, which we already have that included from the other graph, and continues indefinitely upward. Our range is negative 3 to infinity.